finished section 5.1 and I'm almost done with section 5.2 for Anton. So this video will go out on August 21st. I was hoping to get done with more, and I was hoping to finish section 5.2, but it turns out, surprisingly, these are hard problems and they're taking a while, but I want to do them all. They're very important problems, and so it's been it's been a little bit of work to get done the last few problems of section 5.2. So I think chapter 5 is going to end up being 3 videos. I originally had it as planned as 2. I don't think that's going to happen. There's a lot in here and I want to take my time, but I also don't want to make an update that is too big. Of course, I did finish reading the section. Yeah, and this is all the problems that were done before. I don't need to show that again. A point of discussion about the solutions manual, which I never show in all these videos, is I've lately come up with a way. I always want to make sure I don't look at future answers as I'm working through the problems. So when the problems were really easy earlier in the book, I would just do a whole chunk and then grade them all at once. But now, because they're getting harder, and sometimes I make mistakes, I'm making more mistakes for sure, I like to look at the answers almost like odd problem by odd problem, but I don't want to look later, and I'm avoiding that page. So even though I'm showing you this page in the video, I'm not looking at this page because those problems I haven't worked through. And so I've come up with this way of having like a sheet of paper over the next part of the sheet, and that way I can look at this and my eye cannot wander to the latter part. Just wanted to show that. Just a little technique that I've been using. Then for the book, this is gonna be the beginning of chapter 5. I have found eigenvalue problems to be easy the times that I did them in engineering, but that was such a long time ago that I have forgotten how many ways they can be made difficult. And so yes, you're always doing the matrix times the vector is equal to the eigenvalue times the vector. So when you multiply by the eigenvector, you always get a factor. Okay, there's always that eigenvalue is the product. So it comes out that way. That's really what it is, but boy, does it get complicated. So yeah, the various eigenspaces, how many dimensions it has, when you come up with one vector or two vectors or 3 for a 3 by 3, which eigenvalue gives you which eigenvector. And then of course you're constantly adding even more equivalent statements to this long theorem that has been built up section by section. And I believe the only one is lambda equals 0 is not an eigenvalue of A for A being invertible, and all these other rules. Yeah, so even though I would have thought that all these problems are going to be really easy, I was just going to cruise through. No, actually the latter problems of section 5.1 were heavy duty in my opinion, and that's happening also in section 5.2. A new territory, I believe, in the book I have entered. Then of course section 5.2 is so important for me as a student of data science because and I always say it wrong. I always use the wrong terms for the acronym, so I'm going to look it up. It's here. It's in section 9.5, and I think 9.4 is where the theory is laid out. This, to me, is easily the most important section of the entire book for things that I like and that I want to do, and I may showcase them in the channel, I'm not sure, which is singular value decomposition, a very important technique in data science where you take your data and your data is turned into 3 matrices, the product of 3 matrices, and this middle matrix is a diagonal matrix. So everything in here about diagonalization in section 5.2 to me is very, very important. And so I'm going through every single problem, and I will definitely attempt every single problem in this section. I usually do for most sections, but this one is going to get love. And so there's all these similarity transformations that really SVD is one of, is a very special case of. This is just a general theory of how do you show whether two matrices are similarly invariant. And the whole trick is getting your A matrix, doing the eigenvalues, finding this P matrix for it, and then P has to be invertible, and you multiply P minus 1 AP, and that should list off the eigenvalues. So when you multiply out, you do your A, then you come up with the eigenvalues, then the eigenvectors. From the eigenvectors you make your P matrix, then you invert it, multiply it by A, multiply it by itself, and sure enough, the product, that similar matrix, so this matrix is similar to A, will read off the eigenvalues. Great stuff, great stuff. Yeah. And there's complications thereof and tricks for doing powers of matrices. And I'll show how I screwed up some of the problems because I did not realize that in this case, it's not P minus 1 times the matrix times P. It's the other way because you're starting off with P minus 1 AP. Okay, enough about that. Then I'll go and show the work on the problems. And this is the reason why I decided to make this video at what seems like a random point in section 5.2 problems. It's just getting long. It's just getting long. So I think chapter 5 will most definitely be 3 videos and not 2 as I was originally planning. So this is my reading, which of course I just showed you from the book. Made some minor mistakes in the beginning of section 5.1, but it's just straight off work out the eigenvalues. So take the matrix, turn it into a determinant, come up with the equation, find the eigenvalues, plug them, multiply, put in the eigenvalues into your eigenvalue equation, determinant, turn that into a matrix, then find the vector, then multiply the vector times the original matrix and show indeed that it is an eigenvalue. Let me find a good example because I want to talk about this one as well, but for other reasons. And I've gotten to the point where I usually do a line under it to show this is where I did it. And sure enough, you multiply the eigenvector times the matrix, and you get a factor of that eigenvector, and that factor happens to be the eigenvalue. Now, of course, there are a couple of problems where the answers are imaginary, and the answers, they'll just say, well, it's not real, so you don't need to do anything. But I actually worked out a case that was imaginary because I can play with imaginary numbers. Thank you, complex analysis. And so, yeah, just crank through these problems for eigenvalues with that procedure. And that really then, of course, section 5.1, there's more details in the ladder problems, such as trying to get these cubed equations and see how you can break them off into a product of three factors. But in this case, it didn't work out. But I didn't need to do it for this particular problem. Then, of course, a very interesting case of the general case of the matrix A. When you put it into your determinant, you get this equation that is lambda squared minus the trace of the matrix lambda plus the determinant of the matrix, and that sets up a bunch of problems for the general equation of lambda in that case. Yeah, and then the eigenvectors, and yeah, very interesting problems for these. So yeah, and this is why I stopped here, because there's just a lot. Now, in this particular case of showing, yeah, so if lambda is an eigenvalue of an invertible matrix A and x is a corresponding eigenvector, then 1 over lambda is the eigenvalue of the inverse of A, and you still have the same corresponding eigenvector. I did it the hardest way possible, and really the answer in the exercise manual is this long. But they're both the same. I just went the very hard way by actually writing out what lambda was and writing out what 1 over lambda is, and showing that there is a way to show that 1 over lambda is equal to a lambda prime when you set up the equation. You just do the determinant equation for both and you equate them. And there you have it. But I did not need to do that. I did not need to do that. So some of the latter problems for section 1, 5.1, yeah. And I didn't do so well in the true and false. Sometimes I get confused. Then off to section 5.2, okay, which has diagonalization. Doesn't roll off the tongue. So I also, of course, as I read, I actually worked out the equations as I read them to fill in all the steps. Then you get into this business of geometric multiplicity and algebraic multiplicity. So when you have the characteristic equation, like say lambda minus 1 to the cube, that lambda equals 1 has an algebraic multiplicity of 3. And then depending on how many vectors you find, it's how many how much there is for a geometric multiplicity. Then so I just worked out all these problems where you set up the P and then you invert it, then you multiply it, then you get the similar matrix. That's just, after a while, you're doing the same thing. You're taking your A, getting the determinant equation, getting the eigen values, making sure that the correct eigenvectors work out, and then making a P matrix with the eigenvectors, inverting it, and multiplying the P minus 1 and the P with A in the middle, and you get your similar matrix. Just keep doing that multiple times. A successful breakout of a lambda cube equation into 3 factors. There it is. But then, as I was mentioning before, when I got to the power problems, I screwed up multiple times until I finally caught it. I couldn't figure out why my answer was different, and it's because for the power equation, you're actually flipping it. You're doing P matrix to eigenvalues to a power P minus 1. Yeah, see, I caught that here. It's flipped. And then after that, I started doing it correctly. Yeah, and then I'm up to question 28, although I don't think 28 is done. This is just, I'm exploring it. Yeah, actually, I take it back. I forgot. I did figure it out. It's just a specific theorem, and the answer is a lot shorter as a proof than all this playing around that I did. And yeah, there was some, oh, and also I've started to, for when I make videos, is I always forget to talk about something that happened. There's a lot that happens when I work on these problems, is I'll put in these little things as reminders. So for example, in this case, is similarity associative? And it sure is. And the way to do it is to say, well, if A is similar to B, then B is P minus 1 AP. B similar to C, then C is equal to Q minus 1 BQ. And then AC to C is equal to R minus 1 AR. And then when you put them all together, sure enough, because you end up getting a Q minus 1, P minus 1, you can flip it. And then, yes, it does work. It does work that similarity for matrices is associative.